Rob.
Hello.
Avinash.
Good morning.
Come
Did you drive today?
I came up last night.
Oh.
There's nobody for tutoring.
Yeah, I think everybody is just saying, hey, it's Thanksgiving, week is coming, so.
I think one of my tutees was probably a little bit upset with me because I kind of pushed her beyond the watching me do problems. It's like, you're gonna have to,
Yeah, one day they're gonna have to know how to do this.
I gave her homework.
Yeah,
You
you
give her, in tutoring, you give her.
Well, it was to do the same problems that you did, but this time, put your paper aside, do it on your own.
Got it.
And
No, that helps. I'm not, so I'm just saying that you're too good a tutor. You don't get tutors like that. You just, okay, you came here.
Well,
That's done.
she likes to go to all the tutors and just, you do the same thing. So like I do the same problem over. And I've seen the pattern. So this time I kind of flipped it. So I made her do the heavy lifting. Because normally I'm stuck at this point, and so I get them through that point. This time it was here, you start.
Yeah.
You just start from the beginning, and then I said, go through, and I said, write this down in your words, in the way you understand it.
Got it.
I think they should change this tutoring system just a little bit, so that tutors are not there to do the problems for students. They just guide the students.
A lot of the times I'll start out with just putting up an equation and saying,
Well,
do you
same
have
as-
this one?
Well, the thing is, students are used to that system, so they kind of come with you with a lot of expectations that you will do problems for them, and if you don't do problems for them, they're going to be disappointed.
Well, if you have a lot of students, it's tough not to do that. If you've got like most everybody else is doing it online, you got 4 students online. It's an assembly line. And this was a night that she was the only one, and so I had the luxury.
Yeah.
And
No, that is nice. I think one should, it's like you look at the student and it's a student specific thing. And you're probably enough experience that you get within 5 minutes, you know exactly what kind of student he is, how hardworking he or she is.
and they are hard work.
Yeah.
That's the thing, is they're very hard work.
Yeah, that is my
It's
whole.
misplaced work.
Agree. And it's hard to convey that.
Yeah, Avinash.
It's convincing them that they're capable.
Yes, exactly. Yeah. And it's also that sometimes they come in from a different field where the stress is on something else, and then you suddenly come into mathematics or physics. It's slightly different kind of learning. You forget that it's a memorization. It's not the central point.
Yeah, usually people from especially the biological sciences, they struggle.
Yeah. I wouldn't say all of them struggle, yeah, but more of them on average. Struggle. Yeah.
There was a guy in grad school. He was working on his master's degree in math. His undergraduate math degree did not require physics. But in order to get his master's, he had to have calc-based physics. So
The whole of undergraduate physics student managed without calculus.
Well, he had calculus, he didn't have the physics.
Oh, calculus based.
Yeah, he didn't have
Okay,
calculus physics.
Don't you think it's not fair? Like especially when you get an undergraduate in you take a lot of math courses, but if you get an undergraduate in math, you don't take you can survive without taking any physics.
Well, he was on his third attempt at passing the second semester of calc-based physics. And then I had a lady working on her doctorate in biology, and she had to take trig-based physics because she had gotten all the way to that point. And she needed trig-based physics to meet the backward requirements.
Yeah.
I think she was attending, I think it was University of Missouri St. Louis or St. Louis University. I wasn't sure. I can't remember which one, but very capable. But
Was it Washington University in St. Louis?
it wasn't Washington. But some small private schools, they don't require physics because sometimes they don't have the faculty.
That's right. Yeah. Not only private school, even public schools, if you're from a small town, that's what I understand. It was hard for me to realize, but it takes a lot of time for me to realize that different students come with different backgrounds.
I'm probably surprised you I turned in my homework online because I got it done 2 days early and I'm so excited that I submitted it.
You know what you white people say? Overexcited when it's toxic.
Okay, we're all of us, no, not all of us, some of us here.
Moses,
Oh, Moses.
Are you on your phone? Moses?
I mean, I'm
Yes.
sure questions are Moses all the time.
Yeah, I'm having internet troubles today.
Make sure you pan the room so he can see what's in the background.
Yeah, right.
I see a mandala on your background.
What did you say? I can't hear you.
I said I see a mandala on your background.
Oh, yes, yes. I think you've pointed that out before.
Chat for 2 minutes. Let me do this. I mean, this is. Managing. Like, I want to put my mic is here, even though it's connected by HDMI. The sound is not coming from this device. Instead, it is coming from here. It used to be fine until 1 week back.
Is the volume up on the?
I think so. I thought I checked. Yeah. It is coming from.
Can somebody speak?
Hello? Speaking for you.
I think it's coming from TV. Maybe just me.
It's coming from here. Come on.
Is it?
All right, that bad.
Well, I
No.
think it might need to be the settings in the system. Or the-
Settings on this. Yeah, go ahead.
The
Ohio gozaimasu.
I think it's with the computer, not TV.
It's a source.
from there. We're trying to figure out the
Can someone speak?
Hello?
Hello?
Can you hear me? Can you hear me?
Yeah, we can hear you, but we are hearing you on my computer rather than the classroom audio. It's very.
Oh, okay.
Okay, I did press on HDMI.
See if somebody say something.
I think we need the source for this HDMI source on a television. How do you set that? Do you see what I'm saying? On a television, you say source,
I think,
HDMI source. So it's not picking up. Oh, yeah, there you go. So
HDMI.
say something again.
Hello?
But it's audio is not going out on that.
Yeah, that's fine.
Try something. Say something now, please.
Hello?
Hello?
Can you hear me?
Hello?
Hello?
Can you hear this?
Hello?
They cannot hear us.
No, we can hear you.
Okay, he said he could hear us.
We can hear you.
Now let's try. Try it now.
Can you hear us now? On the TV?
Now it's coming out of this.
Okay, now we need to put some volume maybe. Again?
Can you hear us? Is it working?
Huh.
Now we lost it.
there were 3 options, right?
There are 3 options, but 2 of them are clearly not.
Are you using the same HDMI cable as you
Oh,
always
same
use?
as system.
I'm afraid we're just going to turn the computer volume up.
No, that is full, I think.
Are you using the same HDMI
we can't
cable
hear
as you
me.
always use?
Hello?
I think we have to set both settings back to the real tech
Speakers, real tech, right?
and on the computer too.
I think, tell something, please.
Hello?
Yeah, let's manage with this.
Are you using the same HDMI cable that you always use?
Yeah. This is 1 week back. Last Friday, yeah, suddenly it was coming from here and I said, I'll fix it later. And I never got back to it. So today I thought I'd try. I think I should just reboot the system. That might be just what it is.
Could also be that your HDMI cable is not working properly.
It's the same one I'm using since 7 months, and it was a new one when I got it. I doubt that it will be a problem. Usually these things are robust, right? It's pretty robust. But yeah, surely that's a problem. I mean, I agree.
Every time you wind up your cable, you have a chance of messing up the link because the HDMI carries
Actually,
sound.
HDMI cable does not even belong to me. This is from the classroom.
So it just stays there. Okay.
It just stays there. I don't think I can do anything. So probably others are using this room, assuming that.
We don't know what they're doing with the HDMI cable.
Yeah.
They could be wildly mistreating it.
Yeah.
True.
Turning
But
it
I
into a
assume many
last.
people use HDMI. Okay.
We can hear you, which I think is the most important thing.
Okay, good. Okay. Yeah, no one complained in the last 1 week, so I assume, but it's just, at least for me, it is much easier when I'm listening to the classroom audio, but I guess no one else realizes it. It's just me.
Jordan, not being able to hear you, is it not important?
No, that's a good thing. It's a good thing not to hear me. You'll hear me mumbling or you'll hear YouTube videos playing in the background. Or it'll drive you insane because if it's you speaking and you're hearing yourself speak while speaking, it can probably be a little distracting.
I mean, what did you say?
The last class, I was playing audio in the background. I couldn't hear it, but for some reason the class could hear audio of a lecture of Shajesh previously that I had pulled up. Since I was behind, I was reviewing the lectures. And while he was teaching, he was also teaching on my screen in the background, which he could hear.
Lost the
I couldn't
reality.
hear it. So when they were talking about it, I was like, I have no idea what they're talking about because I can't hear it. But then I looked at all my tabs and I saw 2 or 3 videos, I guess, since I had pulled up the web page and just began playing. But my audio was dedicated to Zoom, so I couldn't hear it.
Got it, got it. Okay. Let's see what we can do. Oh, no homework. So new homework probably, homework 10, I haven't uploaded it. So there should be 2 more homeworks, homework 10 next Friday and homework 11, 1 week, 2 weeks after that, right? So this will be November 20th. I haven't uploaded it. So probably. Okay, there'll be 1 more homework and there is a midterm 3.
There's 2 emojis now.
And that's when is the exam?
It should be Monday,
16.
November. Yeah.
Yeah, Monday, right? So it will be a take home, right? Your final exam. Does anyone know, are you guys allowed to be in campus after next week?
I don't think so.
You
I
cannot.
don't think so.
Can I be on campus?
I would say you are not allowed to have classes, but as a student, I might be able to come to campus.
I doubt it.
You cannot. Like what I'm saying is that I was just wondering, I can have classes here, right?
No, you cannot have classes.
But I had a Zoom.
And what he's saying is he can record his class.
Yeah, I can record it. You cannot be here,
Yeah, that's,
right? I think that's what I meant. Yeah, maybe I didn't say it clearly.
Yeah, I'm not sure about faculty. I'm not sure how that works. If it's like a total,
I'll find out. Yeah, I was confused. Yeah, I'll find out. Should be there on the internet, I suppose. Okay.
I imagine faculty would be able to come.
Yeah, because I have to record, right? I can of course do it at home also, but this is much better quality. I think you guys have done it both ways, right? Do you think this is better?
I actually think it was easier to see your video on the board at home.
Really?
Yes,
Yeah.
because the boards are larger here, so you have to
Zoom out?
Yes, you have to zoom out, but if you are at home, the boards are smaller, so it's easier to see.
I can zoom in if you want here in principle, but. Okay, so you guys like it better there. I thought you have a bird's eye view and all that, like that was too zoomed in.
I think the video is just recorded at a low quality. It's like 360p. It's instead of a higher quality.
Tell that again, John?
Your videos are actually recorded in a low resolution. So when you'll notice when you upload them to YouTube, the highest resolution that you're allowed to select is 360p. So when you're actually recording your lecture, you're actually recording it in low resolution, like very low resolution.
No, tell me the difference between last semester and this semester.
Last semester, your recordings were in much higher resolution than this semester. They were like 720p. So whenever you were writing on the board, even though it was closer and not a bird's eye view, you could see, like for instance, whenever I look at your writing on the board now, you can tell that it's low resolution. And even when you walk across the screen, you're somewhat pixelated yourself. It's just, it could be that the internet that you're using is slower, or I'm not sure.
Okay, yeah, good point. I see what you're saying because when I'm uploading things have changed. I did realize that. But it's not 360, it's about 640 or something these days. Earlier it was 10, like 4-digit numbers. I remember that.
Yeah, 1080p most likely, but I think it was 720, but maybe it was 1080. I'm not sure.
Okay, good point. I'll look into that. That helps. But as of now, I cannot immediately conclude anything. Okay.
Yeah, no, it's fine. This works actually. I mean, I'm
Yeah.
following fine.
Yeah, that helps. I don't think. Yeah. The whole semester, the quality was low. Okay.
Well, actually, last semester the quality was higher, is what I was saying.
Yeah, I see what you're suggesting. I do realize that I was using Ethernet, not Ethernet actually. I was too close to the router. So the internet was higher in quality probably. And I do have a good internet connection at home. But I would expect that the internet is far better in the campus. But it's just that I might be farther from the campus. No, it is.
A lot of times,
Mhm.
what you get on large bandwidth,
Like when I upload a video, when
No,
I'm at home,
no.
this takes maybe about a minute. This is 10 seconds here.
Here the upload speed is higher, but download speed.
Same thing, download. When I download a YouTube video, these are big files. Sometimes these are gigabytes.
What's the opposite thing?
but you have to think about your sizes of your files. Here you're recording a 360p video. So the
Yeah.
file size is much smaller than a 1080p video.
David, how about this? I have done recordings at home also. It's significant. Internet, no doubt. I mean, it's faster in my office, no doubt. I don't know about here.
Oh,
But I have
are you
no-
talking about the Ethernet? Yeah, Ethernet is probably faster.
Yes, it
I was
is
talking
Ethernet.
about Wi-Fi.
Yeah, I use Ethernet office. Yeah, but yeah, it's significantly like it's not that it is just it's an order of magnitude bigger.
You're speaking of upload and download speed?
Both, yes. Because I download the file from Zoom and then upload it on YouTube.
I mean, you can do a simple test after class. You go to the computer that you're recording your lecture on.
Yeah.
You type in bandwidth speed test and you see what the speed test says. And then you go home and you do the same. You type in bandwidth speed test and it'll give you an upload and a download speed. You also could be limited to the amount of bandwidth you're allowed to use on like public access, something at the university. They could limit you.
Probably not. I think it's probably university is way better, way better. Like I think that's what I've heard also, and that's what because there are these committees that are formed and they're even upgrading the internet. So I'm aware that the university internet is really good. I'm not comparing it with other universities, comparing it with MediaCom in the city. So way better.
I mean, the internet could be better if people aren't using it, but you have bifurcations at every point or intersection. So
yeah, but
there's only so much access and data can go through those singular
I know
points.
the details. I think that's the architecture-wise way better. It's like I don't know the details. I don't want to get into this discussion too much.
Yeah.
But I'll be surprised that my home internet, even though it is a good one, is better than my office internet. That is really surprising to me. Okay, but okay. But you gave me enough hints that quality was better last semester. Okay, let's do something after 20 minutes. Okay, so what I want to do today and next couple of classes maybe is what is called dielectric models. This is broadly called, I think this is a baby step towards what can be called transport phenomena. Like if you're doing solid state physics or most of the applied physics areas, this is broadly called transport phenomena, but this is a baby step towards that. I mean, transport phenomena is you can study it in as a whole semester or probably a whole PhD course. So that's what we are. as simple as what does it mean? One of the first things we learn in electricity and magnetism, this is a course on electrodynamics, is Ohm's law, right? Where does Ohm's law fit in whatever we are doing? We never mentioned Ohm's law, correct? Where is Ohm's law? Right. So that's the question one asks. Like, how does the materials behave under an electric field? So that's a response. You provide an electric field, and the systems behave in a certain way, and that connects with what we were doing earlier, response to something. And here we want to talk about a specific response, and that's we'll talk about conductivity today. And next time we'll talk about insulators. How do they behave? This gets more involved when you bring in magnetic fields. For example, Hall conductivity. Have you guys all are you familiar about Hall conductivity? What is Hall conductivity? Extra credits. What is Hall conductivity? Or what is Hall effect, let's say? No?
That one, you know.
Yeah,
Well,
I've heard of it, but I'm not familiar.
yes, please, go ahead. Anyone?
Well, if you apply an electric field in one direction and then you have current flow in a perpendicular direction in the material, that's the essence of the Hall effect. Right. If you apply an electric field in one direction, and then in a perpendicular direction, there's current flow in the material.
Yeah, so you apply an electric field in this direction, let's say.
Uh-huh.
There's a current flow in this direction. Right?
Yes.
Don't need an additional thing. Maybe that's all there is to it. But you'll never get. Oh, can you get? Don't you need a magnetic field? I mean, do you? I mean, that's a good point. Do you need a magnetic
I
field?
think so, yeah.
Like Hall effect traditional Hall effect, I know is with a magnetic field, but the question comes, if I exert an electric field in this direction, I can have a current in the other direction, right? With anisotropic materials, I can have current in the opposite, in different directions, but I think that doesn't qualify to be a Hall effect. But you guys might want to check on that. Yeah, Moses, you want to comment?
That was my kind of elementary understanding.
Good. So again, extra credit, that makes the extra credit more challenging, right? If I exert an electric field here and I can get a current in the other direction, I think using anisotropic materials, will that qualify to be a Hall effect? Because Hall effect, traditional Hall effect is you exert a magnetic field out of the board. Let us say this is magnetic field into the board. And then what happens is that the magnetic field tries to, suppose it's a positive charge moving in, right? Positive charge will try to push these electrons in that direction. There's a force to my left here, and electric field is of course causing this to move in that direction, but then all these positive charges collect here, right? And that creates a new electric field, and that tries to balance it. So there is an electric force in this direction, and there is a magnetic force in this direction, and they have to balance each other. Roughly that, yeah. So there's an induced electric field. That's what you're trying to.
Doesn't it relies on the Lorentz force being balanced though, right?
That's correct. Lorentz force being balanced, but more than that, the electric field in this direction is an induced electric field. It didn't exist to begin with, right? This is Q times E. This is not the applied electric field. Applied electric field is moving the charges, but the electric field that is causing the electrons to go to the right is actually an induced electric field. So in that sense, it's non-trivial. There is another case you can do is when you have electric field in this direction, right? So for example, so this is what is called the velocity selector, right? So you have this to be a magnetic field again. And this time the electric field is in this direction. Right, so that's your electric field, and these arrows are your magnetic field. So if you have a beam of electrons, so now have a positive charges, there is a beam of electrons, so you can always throw a lot of electrons, like heat a sample, and there is a lot of electrons moving in, and this positive charge will experience a force or try to go this way because of the magnetic field, but it tries to go this way because of the electric field. And if these two are exactly balancing, then this will not get affected. So that's called a velocity selector. All right, but that's slightly different from this in the sense here there was no electric field, but still it tries to compensate that. So it's an induced electric field. So slightly more, how do you say? It's a response, maybe that's the way to put it. The electric field itself is a response from the system, like the induced electric field. Right? But anyway, why did I bring this up? Yeah, so I was saying we will do simple systems like just a simple conductivity, but you can easily extend, I wouldn't say easily, it can be extended to systems with showing all conductivity, but like conductivity itself, I should say, came up only in the early 20th century, so 1900, 1910. So we will talk about Drude model today. Right? This is a very classic conductivity model. And if you want the same thing for Hall conductivity, it took some time. Like it is not that it came immediately. It waited for quantum mechanics and so on. Even today, if you want to explain magnetism very well, it is not that straightforward. You don't see it in textbooks in immediate textbooks. So it waited until 1950s and 1960s for explaining these phenomena. Okay.
When you think about computer chips using holes and electrons,
That's correct.
without an electric field, I think you would still get the Hall effect, even with having an induced electric field as opposed to an electric field itself. Like, you know.
I don't know. I don't want to comment. Maybe, yeah. It is true that holes have a separate model explaining them. That much I can say. And yeah, let me not comment too much because I don't completely understand. Like there's another effect. This is called spin Hall effect, which is very, it's a big, how do you say it? It's very popular these days. There's a lot of interest in spin Hall effect since topological insulators came up in the last, I think this, in this decade, it's not that it is very old. In this decade, there is what's called spin Hall effect, and there is a lot of interest in it. But I haven't explored it too much, so I don't want to comment. It sounds very interesting. Even I'm interested, but I never explored it too much. So let me not add any comments to that. That's okay. Yeah. Okay, so ours will be very simple. Okay. So what is Ohm's law, by the way? Ohm's law? V is equal to IR, right? So V is equal to IR, very broadly speaking, that's a scalar, right? But let's do a slightly better version of Ohm's law. Let's discuss the microscopic case, right? So let's do V is nothing but E times dL, and let me say this is just L, length of the material, and resistance is, so V is equal to electric field times L, resistance is resistivity times L over area, roughly, very simplistic speaking. That's the rho L over A, but I'll write A here. Right, so current per unit area is current density, and the lengths cancel out. And this seems to suggest that this is standard. This is J, right? Current density times rho, but 1 over rho is conductivity. So that's 1 over sigma. We want to put this all in vector, so our Ohm's law would be J would be equal to sigma. It can be a dyadic. It's like the electric field in the x direction can create current in the y direction if this is a dyadic. So in general, this can be a dyadic. That means to say electric field in the x component can create a current in the y direction, but let's keep things simple. Like we did the response function, immediately we can ask, this is very misleading in the sense, is this time dependent, is this frequency dependent? So we realize that when there are response functions, time dependence has to be causal. And if you want to avoid the causality very completely, then you have to go into the frequency space. It's not that you avoid it, you hide it in the Kramer-Skronic relation. Right? So that's all that is. It's not at all true that you escape causality. So this is our Ohm's law, and let's ask what can we do about this? So how do we get this? So of course, this is an empirical relation, and we will show that this is actually not in time, so this is actually in frequency, or it's best understood as frequency dependent quantity. But then why don't we ever talk about it, right? We never talk about whether it is frequency dependent. On Ohm's law works very well. We do this in labs all the time, and it works very well. Most of the time when we are using it in undergraduate labs, it is zero frequency. So when we think of it as J is equal to sigma times E without mentioning what it is, what we're talking about is this is zero frequency. And omega equal to 0 means what is the time dependence in it? Like what is the time scale? If frequency is very small, what can you say about time? The associated time in the system. It's very large, like it is the inverse of frequency. That means T means the time for which you're observing the system, capital T, not the variable T. So this is very large. So that's static. So this is statics. That's the best you can get. So if you have a time-dependent system and you want to get rid of the time dependence, you observe the system for a very long time, and you hope that the electric field and other fields are not changing with time, but you cannot make it infinity. That's impossible, right? So you can make it very large, which is equivalent to saying that in frequency space, you're making the frequency small, and that's the idea of statics. Okay, but we want to, and again, as I said, Ohm's law is empirical, based on experiments, but can we have a simple model so that we can go from that? Like if we want model work, then you can change accordingly a small tweak and then get it better and better. Right. So we have a crystal, let's say. So this is a very simple model of a material. So we have atoms, correct? So let's say these are crosses all represent atoms. And it doesn't have to be all ordered. Just a very simplistic model anyway. So these are atoms, like cross means atom. And there are electron, or I should say atom plus, what is this called? All the binded electrons, right? So there are various kinds of electrons in a crystal. Some of them are bound, bound electrons, right? Not binded, bound electrons. And there is some electrons in the outer shell that actually can jump from one to the other, right? So again, very simplistic model, but it goes very far. But there are electrons which are free to move, right? So they completely are free to move. When they are in between, they don't experience any forces, but as they get closer to the atoms, they get repulsion, or let's say they get repelled by the electrons in the outer shell. So they collide, right? They come and collide, and it's very hard for them to move, right? So they do all these collision processes, and electrons, it takes a pretty lot of or lots of collision for it to go even a centimeter, even though they're moving almost with the speed of light or at very relativistic scale. They go very slowly. That's what we want to model. We're going to make it very, very simple, right? It cannot get simpler than this. So there is electrons. So this is the mass of the electron. Newton's law. So it experiences Newton's law. Right? So that's mass times acceleration. Remember, electrons themselves are going extremely fast, but we are saying as a whole, there is a motion that can be described using Newton's law. So this mass times acceleration. M is the mass of the electron. What are the forces acting on it? To begin with, we can think of there is no electric field at all, but we want to talk about electric field. So let's begin with exerting electric field. So that's your electric. Let's put that all through. So that's an electric field. We put in an electric field. What's the force it experiences? That's Q times E. If it was a free electron, that's the only force it would experience. But it's inside a crystal, so there are two kinds of forces electrons experience. It depends on whether it is bound or whether it is the conducting electrons, called the free electrons. The free electrons, they are moving, but they're colliding, as I showed. Right? So that collision has to be modeled. So we will say that is having a friction, right? And friction or dissipation, you can say, and it will be again simple. We'll say it's velocity dependent. Right? So we'll say this velocity dependent force. So it's velocity dependent, negative, because it is going to oppose the direction in which you're getting electric field. Otherwise, we'll have perpetual conductivity. We don't want that, or we don't expect that to happen. So that's the negative sign. Then comes the constant, right? We want to put a constant. Since there is an m, I'm going to divide that by m very soon. I put an m to begin with, right? And some material dependent constant, which is gamma here. This is gamma. My gamma is going to look like gamma, but that's a gamma. That's the best I can do. I'm trying, learning. Okay. So that's gamma. What's the dimension of gamma? What's the dimension of gamma?
So it's the -1.
That's correct, right? So 1 over time, so that's time inverse, right? Right, time inverse. Correct. So that's a good thing to observe. And this is going to be the property. Now, we are going to think of it as a material property, but it turns out that there is a more fundamental nature to that. Like this is not really like the typical, like even the conductivity itself, we often associate it as a number associated with different materials, but at a very microscopic level, this seems to be built out of fundamental constants. That's our understanding. Even now, it's not completely clear how it works, but there seems to be a fundamental meaning to that gamma. But for us in this class, it is just an empirical constant, and that's what we'll work with. And that's where the conductivity will also show up. So conductivity will depend on this. Okay, so that's our equation, and we want to solve this. Right? So that's what, but we want to connect this with this. So you would ask, okay, so this is the motion of an electron. how is this going to give me Ohm's law? Right, so that's the connection we have to make. So how does it work? So first of all, let me rewrite. Let me go here. So this equation can be rewritten as divided by mass, put the velocity on the other direction, and I can write this as an equation in velocity. It's a function of time plus gamma. Write it better. Thank you. Plus gamma, right? That's a differential equation for velocity. Then divide it out by mass, so it's electric field. This way of writing it brings out the fact that electric field is an cause and this is an effect. Right? That differential equation gives me that. Let's say that we solve this equation and we get the solution for V of t. That's a solution, which we will do today. So we will spend the time and get that solution. But what if I get that? How does that tell me what's the Ohm's law? But that is, what is this solution going to look like? This will be a function of, this is supposed to be a function of electric field, right? How do you write this? What this? Functional. Okay, whatever. It depends on the electric field. That's all I'm trying to say. Okay. So whatever solution you write, it is not necessary. This notation, this has a notational significance, but I'm not going to use that in this class or even in this course for that matter. But it has a notational dependence in the sense that it is a function of electric field. Okay. So velocity depends on the electric field. So that's what we said, cause and effect. Right? That's okay. But how does this give me the electric field? How does the electric field is good, right hand side? How does the current depend on velocity? Right? Yes. Tell me again.
Drift velocity?
Yes, drift velocity. So this is the drift velocity. Actually, we didn't say that this is the velocity of the electrons itself, and drift velocity is related to the current is proportional to velocity, right? So basically, if you realize J is equal to charge times velocity, right? Here it is E. So let me write that as Q times velocity. That's it. Right? This is time dependent. That's if that's for a single charge. Lots of charges. Right? That material has lots of charges. That's number density. So that's just multiplied by the number of, which electrons are we talking about? We are talking about not the bound electrons, those ones that are free. Two kinds of charges, very simplistically speaking. We said some of the electrons are bound to the atom, others are free to go around, and we modeled it as free to go around. What is the simplicity in the model? Actually, they're not. They hop around and there is something pulling it backward. All that is simplified to just they're free to go. So you say that's free charges. And this is the typical way all the transport phenomena works. You solve for an actual physical quantity, multiply it with the number of charges, and you get a macroscopic phenomenon. A microscopic phenomena and a macroscopic is connected simply by the number density. Like that's what happened in polarization also, right? We said there is a polarization density multiplied with the number density, and you get the electric polarization of the material. So that's going to be our solution. So we want to think of this. So hopefully there is an electric field that comes up. So put in the solution here, and we will identify the sigma. So we are going to substitute this in here. Whatever comes in front of the electric field is going to be the sigma, but this is time dependent. Our sigma was frequency dependent. So there's some we have to work on, but remember, that's not very hard because we have done the response function. How it will show up is this will come out as an integral et prime. So let me not say what's the solution. So this is some f of sigma, right? Sigma of t minus t prime times the electric field. That's what it's going to come up with, right? It has to be causal, so it has to go until T. And that's what is going to happen. And then we will Fourier transform this, and you'll get your Ohm's law. Right? That's what is going to be the strategy. Okay, so that's your 3 steps of motivation. We have a model, so this is a model, solution, and connect it with a property that we discussed with, and that is the Ohm's law. Okay, any questions at this stage? So I'm going to go to the details now. I'm going to solve that differential equation, get the solution, put it in here, and then do the Fourier transform. Okay. Any questions? Okay, so let's quickly do this. So we want to solve this equation. Gamma, which looks like velocity, v of t is equal to q over m. Is this a homogeneous differential equation or is it an inhomogeneous differential equation? Inhomogeneous because we're solving for velocity. Any terms that doesn't have it have as an electric field. So put it equal to 0, that becomes a homogeneous differential equation. And I know how to solve that. That means to say that I can use Green's function to solve it. We don't have to use Green's function to solve this. There are much easier ways to do it. But since we learned Green's function, let's do it, use the technique of Green's function to solve it. Why not, right? So we will construct a Green's function. Again, this equation can be solved in a much simpler way, but we will use the sophisticated way. So we will solve this equation instead. If we can solve this, then velocity will be an integral of this and so on. Okay, but if you want to solve this equation, we need a boundary condition also, right? But this is easy in the sense this is equal to 0. Like delta function is 0 if t is less than t prime. And it's also equal to 0 if t prime is greater than t. That's only 2 possibilities, right? In both the scenarios, this is equal to 0, which makes it a homogeneous differential equation, and that's solvable. That's a delta function property. So the Green's function, p of t comma t prime, this is a linear differential equation, or this is a first order differential equation. It'll have only one constant. So and what's the solution for this, by the way? D by dt plus gamma of some g is equal to 0. What is g?
Decaying exponential or exponential?
Exponential, correct? So you can write this as dg by dt is equal to minus gamma times g. If you want, you can put this in the denominator, various ways of doing this. That's equal to minus gamma times dt. That's log of g is equal to minus gamma of t plus a constant probably. Right, but then g is equal to exponential of minus t times a constant because that constant becomes a. Right? So this is a some constant a times exponential of minus gamma of t. Correct. So that's it. That's the solution. So this can have a solution here or there. So let's say a times exponential minus gamma t. If t was less than t prime, but there is another solution. We separate it by changing the constant. That's minus gamma t prime is less than t. Okay. But if you want to connect these two, we have to have a boundary condition at what happens at t equal to t prime. But that information usually is there in the equation itself. So we actually integrate this Green's function equation at t equal to t prime. So integrate it d by dt plus gamma times g. And that's equal to dt delta of t minus t prime. But where do I integrate from? I integrate from notice t, that is t, and this is t equal to t prime. So I integrate from a very close point here, t prime minus delta and t prime plus delta. And the understanding is that delta is positive. Right? It's a positive small quantity. So this is t prime minus delta to t prime plus delta. And this is t prime minus delta to t prime plus delta. But the right hand side is equal to 1. And the g cannot contribute this term gamma, because if there was an infinite discontinuity, that's not possible, because then it wouldn't give you a delta function. So this has to be a finite discontinuity, and the finite discontinuity is captured by this derivative term. So the derivative term cancels out. That's a total derivative. So that's g of t comma t prime evaluated at t equal to t prime minus delta, t equal to t prime plus delta. That's equal to 1. That's the continuity equation. Again, there is an argument involved here. Why does the integral of g go to 0? Because it can only have a finite discontinuity. If it had an infinite discontinuity, you cannot have a delta function on the right hand side. It will give you a derivative of a delta function. So once that is left out, then you have derivative of Green's function, which is a total derivative that gives me the surface. So that's a boundary condition which A and B have to satisfy, right? On the right side, t prime plus delta is the B having the constant b, because t is greater than t prime, and the up one is the top one is the t prime minus delta. So we have our equation, the boundary condition, to be the boundary condition is g of t prime plus delta comma t prime minus g of t prime minus delta is equal to 1, which tells me that a times e raised to gamma t prime, because t is evaluated at t prime, and then delta tends to 0, minus, not a, right, this is b. Because t prime plus delta is b, minus a of minus gamma t prime has to be equal to 1, which means that b minus a is equal to e raised to plus gamma t prime, multiply out by exponential of gamma. So my Green's function is equal to, first one I leave it as it is, a, right? T, for t less than t prime. For t greater than b, I replace it as a plus e raised to gamma t prime times e raised to minus gamma t. This is for t prime less than t. So I replace the b with a plus exponential, and this gives you a structure t, and this is a times exponential gamma t plus plus exponential of minus gamma t minus t prime. Notice there is no a or b on the right second term. This is t less than t prime. And like always, Green's function has discontinuities, and this can be written as A times exponential gamma t plus. This is there in the second term, not in the first term. I can capture that using step functions. This is a solution of the homogeneous differential equation. I can as well drop this at this stage, but you can keep it if you want. If you want to be rigorous, not really rigorous, it's just going to carry on and get absorbed into something else. Right? But this is not really necessary. Why is it not necessary? Because the differential equation satisfies this, and satisfies the homogeneous differential equation. It doesn't give you the delta function. This one will give you the delta function on the right hand side. This one gives you satisfies the homogeneous differential equation. That means it is. Okay, so now we have G. So what is your velocity? So velocity would be equal to some homogeneous solution, which is let's say alpha times e raised to minus gamma t plus integral of minus infinity to plus infinity dt prime of the Green's function and the source, right? So which is source is q over m times electric field. Okay. And that's equal to, so now I'll see that now there seems to be two arbitrary constants, but they are the same kind. So I'll show that explicitly. So it's minus infinity to plus infinity dt prime. And that's A times minus t plus that's just explicitly writing this. But notice that this actually comes out, right? There is this time. This is t dependent, not t prime dependent. So this can come out. So what happens? So elaborate on that. So that's gamma t plus A times exponential of gamma t. And there is integral minus infinity to plus infinity dt prime of q over m times electric field. Whatever this is a constant, right? This is slightly off in the sense that it seems like it depends on the source, but whatever that is, when you integrate it completely, that's t prime independent. And that has this interpretation that future can affect upon. But if whatever this is, the boundary conditions can cancel this out. So this is some arbitrary constant at this point. That is how it should be interpreted. And this is minus infinity to plus infinity dt prime theta of t minus t prime. So this is our Green's function. For all practical purposes, this is the Green's function. This is just a homogeneous. It's Monday?
Friday.
So you leave on Friday? Oh.
Friday I have to go on.
Oh, I see. I thought it was Monday. Sorry. Oh, Monday is the exam. Yeah, that's why we asked. Yeah, okay. 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 So, what was I doing? Yes. So we have here, and then we have q over m times electric field. Okay. But notice, as I said earlier, that this is a constant, so this whole thing can be absorbed into one constant. So we have velocity vector. So all this can be redefined in a new constant. So this is v of t is equal to some constant. So let me say this is v naught, has to be vector, right? And e raised to minus gamma t. No, not a time dependent quantity. That's it. Right? And plus, that's your dt prime exponential, step function. T minus T prime and electric field. Let's see what happens when T is equal to 0. Right. When T is equal to 0, that's right here, correct? Or at T equal to T prime, maybe that's a help. T equal to 0. What happens if T equal to 0? Or T equal to minus infinity. How about that? Does that make it better? How do I set my V naught? The system begins at T prime is equal to minus infinity. Velocity at T equal to minus infinity. Minus infinity. What is this? Oh. Yeah, that goes to 0, right?
No, with and minus infinity.
No, that goes to plus infinity. Minus infinity. So
minus infinity.
Did I get this correct? Was this minus? Yeah, it is, right? Shift, it was necessary for it to go. How do I set my V naught? Help. Okay, one more step, just so that I get more time. So this is e raised to minus gamma t. This is a step function. T has to be greater than t prime. So this is equal to minus infinity to t dt prime, and exponential of gamma of t minus t prime times the electric field. Okay. That's just that's good to see it like this. Then you see the causal nature coming up. But we're going to identify this as sigma very quickly. Correct? Okay. Yeah. So let me see the following argument. Okay? I'm not sure about this. Let's say my system begins at t equal to 0. At t equal to 0, what's that equal to? Okay, so v of 0 is equal to v naught plus at t equal to 0. That's minus infinity to 0 dt prime e raised to plus gamma t prime field t prime.
Should be dt prime.
dt prime. What I say, the electric field itself. Yeah, what if I say the electric field itself? Oh, yeah. Okay. Yeah, you can know how to say this. Yeah, okay. How to argue this out? Yeah. What happens when electric field is 0? Yeah. I think this is the argument. So if electric field is 0, I should have V of t is equal to some V naught, whatever your initial velocity is, times e raised to gamma t. And then you can also ask, what is t equal to 0? What is e equal to 0 and v equal to 0? That's V naught. So that gives us an understanding of what that V naught is. That was why I chose that to be V sub. So that's your initial velocity, or remember it's the initial drift speed. Without the electric field, if there was an initial speed, then it will decay off. But if there was no initial speed to begin with, it won't survive at all. So when you do put in an electric field, you start with the assumption that V naught is 0. So you don't want to have any initial drift speed. So you begin with an initial condition. So that's your initial condition. So initial condition is that there is no drift speed to begin with in the absence of the electric field. So when electric field is not there, drift speed is not there. So our solution is, for our practical purposes, is this. This is what we are interested in. Right. So now let me put back my infinity there, dt prime, and there was a q over m also here. Sorry for that. So q over m, and this is q over m times exponential minus gamma t minus t prime. And that's what I said, that we will have a solution of that kind. We are interested in the current density. Current density is simply free charges, number density of free charges times the charge. We are talking about electrons, so let me bring in E. This is also E, so Ne square over M. So that's given a special name now. We'll call that the plasma frequency, but as of now, that is stated. So that's minus infinity to plus infinity, dt prime times e raised to gamma t minus t prime times electric field. Redefine. We will define the conductivity in the time domain to be, so conductivity in the time domain, t minus t prime, we can all even say it is t. Right? So that's equal to nf e square over m times exponential minus gamma t. So that's your conductivity in the time domain. But this is interpreted better in the frequency domain. So let's go back and see how this looks like in frequency domain. We do know that if you have a functional dependence of this kind, mistake, right? What was the mistake? When I went from here to here, right, I changed the infinity. That should have brought in a theta function there, step function there, right? So this has a step function in it, t minus t prime, right? So this has a step function in it, t minus t prime, and this should have a step function in it. Okay. So this is dt prime sigma t minus t prime times electric field. But we have already shown in our earlier lectures that this relation in the frequency domain becomes algebraic. This becomes omega times electric field omega. But then our question is, what is the conductivity in the frequency domain? So that's obtained by simply Fourier transforming omega t times sigma of t, right, which we already know. Right? So we solved for the conductivity in the time domain. We just have to do this integral Fourier transform of this. Let's do that. So that's minus, that's equal to, so that is nf e squared, this is called the plasma frequency, times minus infinity to plus infinity dt e raised to I omega t, that is e raised to minus gamma t, and we have a step function. This survives only when t is greater than 0, so there is a lower limit gets killed. F e squared over m, 0 to infinity dt, and this is t times I omega minus gamma. This integral is immediate, right? Exponential at infinity does not contribute because of this decaying factor there. And at 0, which is coming with a negative sign, this actually is e squared over m times 1 over, it is gamma minus I omega. Is that correct? Oh. Check this, but I don't have. Nice. So I have to do that again. Okay, so that's easy. 1 over I omega minus gamma, and then exponential of t I omega minus gamma. So that's t equal to infinity, that goes to 0. At t equal to 0, that's 1. It's coming with a minus sign. So that's correct. Okay. So that's your conductivity, right? The simplest conductivity model you can have, and this is called the Drude model. It's a pretty good model. It explains a lot of stuff, but yes, still the first model. There are slightly better models, but it's very hard to go beyond this. Okay, so that's good, but we also had, so this pretty much completes our Ohm's law, but I can say a few more things. When this has to satisfy the Kramer's chronic relation, right? Because we killed our t in the upper limit, so it goes into the susceptibility function or the whatever decides the causality. So this has to satisfy Kramer's chronic relation. So we need the real and imaginary part. So let's get the real and imaginary part. And f e squared over m, I just try to multiply by positive, right? So it is positive omega. So it is gamma over gamma squared plus omega squared plus I times omega over gamma squared plus omega squared. So that's the real part. That's the imaginary part. And so there's one thing, what should I show you? Yeah, so remember your real part of sigma omega has to satisfy the Kramer's chronic relation, which is minus 1 over pi times minus infinity to plus infinity d omega prime, and that is what was your, so this was omega minus omega prime squared plus what was Kramer's chronic relation? So that is delta square, right? Plus delta square, and that is imaginary part of sigma omega prime. And I'm not sure if there is an omega minus omega prime in the numerator. I think it is there, right? There are various ways you can write it. I think the way I showed it to you guys, this is the Kramer's.
I think we also have to take the limit.
Other
Delta goes to 0.
limit delta tends to go to 0, right?
Yeah.
Okay. I'll stop here by saying that this indeed satisfies this. I think this is part of your homework. Is this part of your homework? Have you guys looked into the homework? You guys said no. It was due to me. Nice. Okay. But this was, I think this is part of your homework, and I'll let you guys do that. There's some more things you can do. There is one more property that this satisfies. It is kind of nice. This is called, what is this called? This is called a sum formula. So this is equal to a constant. Like if you normalize this correctly, this is equal to 1. So this is called a sum formula. And these are all indications of very fundamental properties of this dielectric models. In fact, you make it take it to the extent of a postulate. You say that it is necessary that you have these models have to satisfy that. So I'll stop here. I would have liked to do a few more things on that, but maybe next time when I come, I will start with this and do some properties of this. And then as a similar model, we can construct for insulators, and which is called the Lorentz, Drude Lorentz model, and we will maybe do plasma model also and stuff. Depends on the last week what I want to do. Okay, thank you. Hurry a little in the end.
Say that again.
I had to hurry a little in the end.
Oh, okay.
We have Avinash here, Rob, I believe.
It's just me.
So in all your classes, you're the only one in the class? Because you said yesterday after my Zoom class, you're the only one in the class.
In person.
In person. Okay, guys.
I try to utilize any excuse that I get to
Get out of the house. Yeah. Understandable. I can relate to that. But these days I have family, so changes. Yes.
Just to clarify, on Monday, they're gonna have the class open.
We will have the class open in the sense I'll be there on Zoom. So you guys are free to come, but if you don't show up, I won't mind. How do you say it, behind the schedule? No, in the sense that I have shortened many things. So how is it behind the schedule? I would have liked to do a lot more examples on polarization. Right? So in that sense, we are behind, but we cover everything. I do cover everything because I have to start magnetism next semester. So in a sense, yes, because another thing is that the conservation theorems that we studied in the right at the beginning, that is typically done in the second semester. Traditionally, that's done in the second semester, but I start with that. So we have more time in that sense. But I plan to rush on magnetism the next semester. My idea is to maybe not spend too much time on magnetism and maybe do a little bit more of relativity and radiation. So that's my thought, but we'll see how it goes. So yeah, we are not
Next semester will probably be smoother for most people as well, because they won't, I think most people are in both of your classes. So with the 3 exams in each course plus the homework, I feel like it's tough to
Yeah.
keep up a little bit right now. But next semester with just your 1 course, I think it'll be
Ah,
a little bit easier to probably stay on track, be my guess.
but others might do classical mechanics, right?
Oh yeah, I forgot. Yeah, not me.
You may not do it. Yeah, yeah.
I survived last semester.
So you guys are saying the 3 midterms that comes parallelly, that's hard. So what if I split it 15 days apart all the time?
I think it's just difficult because you're you have to reframe your mindset when you're preparing for the exam.
Yeah.
And with the expectation that it's going to be in class, you're preparing as though it's in class. And then, so when you're focusing solely on your homeworks, when homeworks approach an exam, you're trying to, not forget homework 1, 2, 3, and still complete homework 4 while preparing. So you're completing homework 4 while preparing for the exam. And then when you have 3 exams, those exams come at such a point where if it was just one of your courses, it wouldn't be bad. But with 2, you have to think that's 6 exams plus continuous homework in each of them. So when people are taking 2-year courses, it's a lot of actual work. And I think it's a little bit more difficult because it's much harder to, if I want to ask Moses a question now, I don't see him on campus at all. So just that interaction that isn't there makes it a little bit more, he may give me some insight while passing by him in the hallway that just makes me be able to complete the homework and understand everything in the moment. But without that interaction, it's, hey, we communicate via email and try to figure out when people can meet. But oftentimes, not everybody's able to, it's more difficult, I would say. So 3 exams plus all the homework and 2 courses, I think it's a lot of work, especially if you get behind it all. It gets, I feel like I'm drowning almost at this point. So.
Yeah, I might make it 2 exams next semester, by the way, at least for ENM2. Not sure about classical mechanics.
I also feel like for those of us teaching 253 labs, that the plan for next semester logistically is a lot more sound than it was for this semester. Like I feel like this semester was really chaotic with just like which students can be where and when and how to communicate that to them. So I think that stress will be a little bit relieved for next semester as well.
Okay, that's good to know. That's very good to know. Yeah.
It's the same with the 100 courses as well, because we didn't know if we were going to be in class or not in class. Students didn't know how to do their submissions properly almost at all, even though they had some experience, I'm guessing, last semester. But, and then just creating the lab content is also another thing that has to be done for every single lab because it's not pre-done. I think we had one that Moses did last semester, which was helpful. Gave us a little break this previous week, but normally I'm doing like an hour lecture for each lab and then doing all the grades and stuff for the grading portion that I have to do and then the lab grades. So it's a lot to keep up with at the moment, but plus you have to get that sort of stuff done. So if I'm thinking like, do I complete my homework or do I get these grades up for these like 60 kids that need to see their grade to find out if they need to drop before the drop date? Well,
no, that's important. Yeah, yeah. And I was missing on the fact that, yes, you guys also are teaching in a new mode. So it could be a significant stress. I know that because just changing the mode changes a lot of stuff. It's often hard to convey that point, but that's a significant amount of time and stress. Yeah. So yeah, hopefully it's better. And probably first time when you see the styles, like surely Jordan and Moses had taken my class, but others just not knowing what kind of style I teach with and how much lenient I am with homework. All that gets time to get used to. So in the beginning, maybe first few weeks, you guys are all more overwhelmed. Or less overwhelmed because you don't postpone homework. Now you got used to oh, he's the lenient, you don't have to do the homework.
Yeah. And I think your course, differing from other professors that I've had, is essentially the feeling of getting behind in your course is not that you're not getting exposed to the content. And some of the other professors, I would say, like, it's on your onus to not get behind because you have one homework assignment the whole semester and one exam before the final. So you may have like one midterm and one or two homeworks. And you get behind in those classes because you slack, I suppose. So your course is different. You can't really slack. Like, you're getting exposed to the content, but you may be behind of where you actually are teaching in the moment. So like today, when you mentioned the homework that's due today, I think probably most people maybe are just now getting a chance to even probably look at it today. Be the first day that probably most of us have even had a chance to look at it. So we're getting exposed to the material, I think, in your course, which is a good thing.
Yeah, that is what I also go with. My experience is that I don't expect everyone to master every homework problem that I have given. There are very few students I come across who really manage to do that. Full manner, very few students. So, but they get close, like almost every semester you get one student who gets very close to. But, it is a big topic, and that's true for any subject, I suppose. To master the course is entirely different. Like, even I don't consider myself to be a master, so not at all, not even close.
It is nice how you're teaching these two courses together, though. I would say there is a benefit to taking them at the same time, in the sense that I guess you're exposed to similar things, maybe at different times slightly, but when they're brought up in the other course, you have some sort of exposure to it more than likely, or you can see the relation. So it's nice, like green function and stuff like that.
Alia and Michael, you have anything specific to add on to?
No,
not really. Just still behind.
But Alia has commented on certain things whenever she comes for homework. So yeah, the help sessions, yeah. That's why Avinash, you were saying Rob misses on to the other class, you're saying. Yeah.
yes.
But he puts in more time, so he goes in. And he has experience. Okay. Are you guys available on Tuesday of Thanksgiving for 1 hour?
I think so.
Yeah, Tuesday the 24th.
Is it 24th? Okay, 24th.
Yeah.
What will be a nice time? 3 o'clock?
I'm using the Thanksgiving break to just catch up on anything. So I've already taken that week off from my other job too. So I'm available whenever.
Yeah. I'll hopefully send an email this weekend and see if we can, some of us can get, it won't be the whole department. I won't be sending it to the whole department. Those with whom I interacted this semester. So that's what I do. So probably 10 or 12 of you guys. Okay.
Sounds good.
Cool. And if you don't show up, no problem. You won't lose a grade. Okay. Okay. Enjoy, guys.
Thank you.
Thank you.
Yeah, you too.
Bye, guys.
See you on Monday. Wait, yeah, Monday.
Yeah.
Yeah, see you Monday. Yeah.
See ya.
Yeah.
Yes, yes, but, you forget it's a weekend because there was this Wednesday off, right?